You know, the methods for making things in society have their roots in technologies and capabilities that were frankly figured out centuries and arguably millennia ago. Take, for example, molding products. This was invented a long time ago, and when you think about making things today in our manufacturing economy, the world's manufacturing economy is about $12 trillion, and polymers represents about 1.1 trillion of that, and 30% of that's injection molded. And that's using a technology that's been around for a long time. These tools become increasingly complicated to make sophisticated products. It often takes a long time to actually get your hands on these molds. It's not uncommon for them to cost $1 million, make 8 parts for like an electrical connector, and once you have them, you don't want to make changes. And again, this is a big part of the economy, and what's fascinating is because of the nature of molding, the complexity of the process and the tooling, it actually stifles innovation, because once you've invested all that time and money, you don't want to make those changes. You got to reap the ROI on that. The products, because of the challenges of molding, are not as dematerialized as they could be. They're not as lightweight and as strong as they could be. The materials are actually better than the molding processes. And it has triggered cumbersome and energy-intensive supply chains, and there's almost no recycling. Thinking about supply chains, I love this quote from Thomas Friedman: on any given day, 2% of the world's GDP can be found in transit in some way. And that reinforces the global supply chains of shipping products over long distances. And not only shipping products, because of the challenges of making things, we have ballooned up warehouses full of products that are often climate-controlled warehouses around the globe that are actually tying up billions and billions of dollars of capital just waiting for these products to be consumed or needed, as opposed to being just-in-time manufacturing and the opportunities for a warehouse in the cloud on demand. So people have been talking about 3D printing for a long time because it can make these dematerialized products. They can be light-weighted, they can be personalized. The challenge is that historically the way 3D printing has been practiced, you could argue it's actually 2D printing over and over again. There are mushrooms that grow faster than most 3D printed parts. Because of the layer-by-layer approaches, there's a orientation dependence on properties that makes it really challenging to use a lot of these products. The layers and particles are typically not well fused, and the material choices have been incapable of making final parts. A long time ago, we were inspired by Hollywood. And as a chemist and working with physicists and others, we were wondering, why can't 3D printing look more like this? Where objects can grow out of a puddle in almost real time to have amazing performance characteristics. Now, that's a long shot to be thinking about, but we invented a process that we reported in Science back in 2015 that is actually a breakthrough in how one uses and develops 3D printing. It's a breakthrough in material science related to this window at the bottom of this reservoir that's not only optically transparent, but it's permeable to oxygen. And so what happens is when you lower a platform, the build stage, into this reservoir of liquid, it gets very close to the window, and then we start projecting light. And where the light hits, it cures the resin. But here's the catch. The part will bond to the platform, and it lifts the part out, but it doesn't bond to the window because the oxygen's also coming through, and the oxygen inhibits the chemistry right at the window. And what this means is that we can start sending patterns of light that would be impossible to mold an object. And as the part is elevated, it's drawing resin in underneath it rapidly. And this allows a 3D printer to operate 100 to 1,000 times faster than a traditional 3D printer. And this opens up the opportunity for now making things with light. And we study this process in great detail. This is an image called optical coherence tomography. It's kind of like ultrasound imaging. And what you can see is this gap between the growing part and the window that's created by this oxygen that's also coming through the window as the light penetrates further and cures the part and creates this object. I think of this process as a software-controlled chemical reaction to grow parts. And every step of the process we have complete control over. And we now converted this capability into a commercial printer. These are the printers, different build areas, different sizes, different capabilities. And then you can start stringing together these printers into a beginning of a factory-like setting. And the factories can get larger and larger. You can start stringing together the printers. And now you have a capability of giving people a manufacturing tool set that can do amazing things. And here's a video.
We salute all those who believe good enough is never good or enough. Those who pursue excellence for themselves and for our planet. At Carbon, we apply our craft using science and technology to push limits and realize products unmatched in performance. Our difference is one you feel, and it is light years ahead of anything else out there. You feel it in running shoes that control energy with every stride. Saddles that enhance your performance and comfort mile after mile. Helmets that increase your protection every time you take the field. Clear aligners and dentures that improve oral health and give you more than a few reasons to smile. Crafted by Carbon is a promise. It stands for dedication and focus to crafting what you and our planet truly need. Ongoing creation of amazing answers to our toughest questions. We salute the leaders, dreamers, and doers who keep creation in motion, who boldly imagine a brighter future and craft it every day.
So this technology has now been commercialized and extended into some large volume manufacturing, from running shoes to over 1 million people wearing their first 3D printed dentures. And it's just the beginning. And when we start looking at the different buckets of opportunities going forward, we still want the printers to go faster. We want to do multiple material printing. We're already using bio-based feedstocks. We've now figured out how to start recycling the resins, have the products turn back to liquid that can be reprinted. And the opportunities for doing high-resolution printing are quite clear. And this is a big direction where we're going to drive some new technologies. We always like to print the Eiffel Tower as an example. This is the Eiffel Tower printed on those commercial printers. But now my students and I at Stanford have built printers that increase the resolution, and we can make smaller and smaller objects. And if you can see that really small one right there, that's made with a printer with 1.5 micron resolution. So a red blood cell is 8 microns in diameter. And what we're able to do now is start combining these technologies, and we really want to focus on making things easily from 1 to 1,000 microns, which is a really hard spot to work on, including microneedles for delivering liquid and solid products into the skin, and new ways of sampling products from the skin. And so one of the areas that we want to do is, instead of focusing on blood for surveillance of people, we want to focus on the clear fluid in the skin, and where we can do it just with a simple patch and open up much more rapid measurements. The ability of combining these microneedles with biosensors, building on what continuous glucose monitoring is, but now looking for 15 molecules, not just glucose. And finally, new ways of delivering vaccines directly into the skin with the dry product that could be shelf stable and not need refrigeration over long distances. So we're very excited about the future and where this technology can go, and thank you for your attention.